Okay, so a couple things. Um, Let me move this around. So again, we are starting with our next section, which is spheres. There's a few things from before that. Again, I'll show just like I have the last few times. And this is our calendar. Next test is going to be on May 15th, which is still just over 2 weeks away, about 2.5 weeks. Again, it's being tested on those first few topics. The last two topics will not be on that test. Again, if you haven't already printed off this reference sheet, I highly recommend that you do. The equations that we'll be focusing on today are going with a sphere and a hemisphere. Now you will notice that today we will talk a little bit about surface area. On Friday, there's going to be our main focus on surface area equations for the rest of these figures. But today, within the chapter for sphere and hemisphere, they do both volume and surface area. So we're going to talk about those 4 equations during this section. Now, the first example that's in the book is really confusing, and just reading through this, it probably wouldn't make much sense. They are trying to explain things very algebraically. They use a lot of different formulas to show how the equation for a hemisphere relates to the equation for a cylinder and a cone. I think it's much easier to try this first before actually looking at that. So let's go ahead and do the try it first. So if we wanted to find the volume of these 3 solids, notice, well, in order to find these 3 volumes, we need to know the equations for these. So let's go ahead and write out the equations for each one. We have, for the hemisphere, volume equals, oops, I almost did a full sphere, 2/3 pi r cubed. Oops, I said cubed and wrote squared. Cubed. For the cylinder, again, you could just say base area times height, but since it's a circle for the base every single time, we can plug in the formula for area of a circle. So pi r squared times height. For the cone, very similar to this one, except it's 1/3. So volume equals 1/3 pi r squared times height. Now, just looking at these equations, you might get a feel for what's going to happen here. I think it's easier to see when you look at the actual equations in this format compared to what they did in the first example. But we have these equations, and if you notice in these examples, it's very important that you notice that the height in these two is the same as the radius. And the reason why they're showing it like this is to help explain the reason why there's this common connection between these 3 equations. Because if you look at the equation and think of, well, the height in the second 2, and in both the cylinder and the cone, is actually also just r, the radius. So if we represented that as r, the radius, we'd be multiplying another radius, which would make this r cubed. And same thing over here, this would also make this r cubed. So they look very similar to our hemisphere formula. The only difference is the cone is 1/3 of our cylinder, whereas the hemisphere is 2/3 of the cylinder. So now that we see the equations, let's do some of the math just to show that that's how it works. So we have, for the hemisphere, we're going to plug in the 10. We have volume equals 2/3 pi r, which is 10 cubed. So 10 cubed, that's 10 times 10 times 10, that's 1,000. So 2/3 pi times 1,000. Multiply it to the fraction. So we have 2 times 1,000 is 2,000 thirds times pi. And again, it doesn't matter if the pi is next to it or above it. We're going to leave it in terms of pi. Now, this won't reduce nicely, so I'm just going to leave it like this for right now. On the next one, we have V equals pi r, which is 10 squared, times height, which is also 10. Again, we get 10 squared is 100, times 10 again is 1,000. So we get 1,000 pi. On the cone, we have our formula is 1/3 pi r squared times the height, which is 10. So radius is 10, height is 10. So now I get 1/3 pi r squared is going to be 100. 100 times 10 is 1,000. So again, we get 1,000. And if we wanted to change this and simplify it, 1,000 over 3 pi. Now, I take a moment to stop and look at our equation at a certain point in each one of these. Notice the best comparison, if we look at it right here, and right here. Notice the one in the middle is 10,000 times pi. The only difference between these other two, this is 1/3 of the 10,000 times pi, and this is 2/3 the 10,000 times pi. So again, the cone and a hemisphere together, if they have the same dimensions, would equal a cylinder. So there's this relationship. So now let's go back to that first slide, because now this might make more sense. So what they're trying to show here is that if we took the cylinder, subtracted out this cone, the area that's left at this height is going to be the same as the area at this height. And it's the same all the way through. So you can use Cavalier's principle on this as well, because at every single height in this hemisphere and every single height in this composite figure of a cylinder minus a cone, you have the same exact area, which means that we can use the idea of Cavalier's principle to say that these two must have the same volume. So if you have a hemisphere and a cylinder minus a cone with the same dimensions, then you're going to have the same volume. So again, a little bit of a strange concept, but that's how it works. And that's how we can also prove the formula for a hemisphere. All right, so we're gonna move on. Again, there's no point in dwelling on that for too much. That's a little bit confusing. The main thing that you need to do with this equation is be able to use it. So now you'll notice this equation is slightly different than what I just had on the screen. We had, no, it looks like my cursor got in the way there, but this it says 4/3 pi r cubed. This is for a sphere, not a hemisphere. So again, if we're talking about a sphere, instead of saying 2/3, it's going to be 4/3. So for a sphere, let me just write it over here again. Oops, I forgot my P. Sphere. The volume equation is 4/3 pi r cubed, whereas a hemisphere is 2/3 pi r cubed. Again, in both cases, the radius is being cubed. So again, that's one equation. Remember, you do have that formula reference sheet that you can use as you're going through problems on this. I'm not focusing so much on the memorization of these formulas this time, since this is all virtual. And again, you have the formulas on that reference sheet. Use the volumes of a sphere to solve problems. So now this example is actually getting to another concept. Not only do we need to know about our volume in this problem, but we also need to know something about what's called surface area. The surface area of a sphere can be found with another equation, and I'm just going to show what they did here. First, they used the volume equation to figure out what the radius is, but then in order to figure out how much material they would need to cover the ball, so what the actual surface area is that needs to be covered, they had to use another formula for what's called surface area. And again, that surface area formula is right here. it is this 4/3, sorry, not 4/3, that's for volume. Our surface area one is 4 pi r squared. So again, the equations here, very similar. Both the volume equation and the surface area formula both have a 4 in them. They both have pi, they both have r. But then instead of having it cubed, like in the volume formula, it's squared, and there's also no 3 under the 4. So this is, again, our equation for surface area, which again is on that reference sheet. So let's take a look at actually solving a problem where it says, what is the largest volume a sphere can have if it's covered by 2 square meters of fabric? Well, we're going to have to do 2 things on this problem. First, we're going to have to use our volume formula, which again is 4/3 pi r cubed. But we're also going to have to use the surface area formula, which is the 4 pi r squared. Which formula do we actually use first? Well, the only measurement that they gave us was this 6 meters squared of fabric, or 6 square meters. So since this is in meters squared, we know this is talking about area covering the ball. So the surface area of the ball is covered by 6 square meters of fabric. So we have to use surface area first. So we're going to use that surface area formula and plug in. So we're starting here. So 6 equals 4 pi r squared. We need to solve for the radius so that we can plug into the formula. All right, first thing, we can go ahead and get rid of the 4 by dividing it off. So we have 6 divided by 4 equals pi r squared. I could also get rid of the pi by dividing it off. 6 over 4 pi. Now, I'm not getting rid of anything just yet because we may be able to get rid of them a little bit later on here. So what I mean by that is we might be able to simplify this by plugging it into the other formula at the end. So let's keep going with it. We have 6 pi. Gotta get rid of the square, so we're square rooting. Yeah, not a very nice looking problem. Maybe it'll get easier when we plug it into the other formula. If not, we might want to just change it to a decimal answer, which again, right now it's set up that we can just plug it straight into a calculator. But let's just plug it in over here and see what happens. I'm plugging in this whole thing. Well, it doesn't really work out perfectly. If this was a squared, it all cancel out and work out nicely. It doesn't. So let's just go ahead and figure out what that number would be. All right, we got 6 divided by 4 pi, oops. And I'm using 3.14 for pi. And again, we also had to take the square root of it. So let's just go ahead and simplify this right now. We have 0.69 for our radius. So again, instead of having that mess in there, let's go ahead and plug that in. 0.69. Now, I'm not actually rounding this off. I'm keeping that number in my calculator because now we're going to cube it. And if you only went to 0.69 and you keep any other decimals, your answer might be a little bit off. So we're going to cube that answer in our calculator, which gives us 4/3 pi, and then we have 0.33. Again, I'm still keeping it in my calculator so that I can multiply with it. So times 4 divided by 3. That was me multiplying by that fraction there. So 0.44 pi. And finally, if we multiply out that pi times 3.14, our final value here is 1.38. And this is in meters cubed because this is volume. All right, again, not the easiest problem. Now, the other thing that we need to talk about is how do the two equations differ. So I already mentioned it on one of the previous slides, but again, hemisphere is half. So a hemisphere is 2/3 pi r cubed, whereas the entire sphere was 4/3 pi r cubed. On here, the other thing that we need to know before we do this problem, when they talk about a great circle, so this is actually a definition that you should know. A great circle is the largest circle that can go around a sphere. So this dotted circle here that goes around the middle of our sphere is what we call the great circle. The equator would also be an example of a great circle. It's the largest circle that can be made by going around a sphere, and it is also always going to pass through the center of the circle. So there's more than one great circle that you can have in a sphere, but it's any circle that's going to be on the same or have the center point on a plane with it. So on the question now that they're looking at, we have the hemisphere up at the top, has a radius of 4. All we have to do is use our equation. So volume equals, instead of 4/3, 2/3 pi r cubed. Plug in that number, 2/3 pi r is 4, 4 cubed. 4 times 4 is 16. 16 times 4 is that 216? Let's double check before. No, I did the wrong number cubed. All right, that's 64. So 64, we still have the 2/3. 64 times 2/3 times 2 divided by 3. It's not going to come out to a whole number. We get 42.6. Repeating, multiply out that pi times 3.14, 133.973, and the 3 repeats. So that would be our volume. Any questions? Oh, I see one question there. How did I get 0.69? Let me go back. Is it on this problem? Yeah, you're talking about this 0.69 here. Again, actually dividing this out. So if I was to do 6 divided by 4 pi, and I use 3.14 for pi, 3.14, you get 0.47, and then that square rooted gave me the 0.69. Okay. All right. Any other questions so far? Again, most of this section is all about using equations. So you have the equations, so it's a matter of being able to plug into them. So here, again, talking about finding the volume of a hemisphere. The first one is finding the volume of a hemisphere with a radius of 3. So again, both of these are going to be using the same formula. For a hemisphere, volume equals 2/3 pi r cubed. So for part A, we're going to plug in the radius of 3. So volume equals 2/3 pi 3 cubed. So we have 2/3. 3 times 3 is 9, times 3 again is 27. So then multiply that by 2/3. Or again, you can either multiply first by the top and then divide by 3, or you could divide first and then multiply by 2. Either one works. So 27 divided by 3 would bring us back to 9. 9 times 2 is 18. This would be 18 pi. That's a nice answer in terms of pi. Again, you could leave it like that. Or if you wanted to round it off, multiply it out by 3.14. 18 times 3.14, give us 56.52. Again, either one of those are acceptable as an answer. Then we have, for the next problem, what is the volume of the hemisphere with a diameter of 13? Now, again, keep in mind, they said diameter, not radius, so you need to go ahead and change this to radius. So it's only going to be half of that when we go to plug it in. So 6.5. Again, it's the same exact equation again. So volume equals 2/3 pi 6.5 cubed. 6.5 cubed. Not going to give us as nice of a number as the last one. It's 274.625. Multiply it by 2. Divide by 3. I'm using the calculator this time because these numbers are a little bit bigger. We're going to have to start rounding. That's 183.08, my bad, 083. Still got to multiply by pi, so times 3.14 gives us 574.88. And again, that's a rounded answer, and this is in centimeters cubed. All right. Any questions on that problem before we move on? I see Ted has his hand raised. Ted, I'm going to go ahead and unmute you if you have a question.
Hey,
You have a question?
on that question for part A, how did you get 18 pi feet cubed?
So for the 18 pi feet cubed, we have 2/3 pi times 27. Are you good with up to that point?
Mm-hmm. Pi times 27, right?
Yeah. So what I did, again, I skipped the pi for the time being because I like to say that to the end, because if we can leave it in terms of pi, again, I want to be able to show my answer in terms of pi as well. So I did the 27 times the 2 and divided by 3. Now, you could also keep the numbers smaller and do the division part first and then the multiplication. Because when you multiply by a fraction, you're multiplying by the top and dividing by the bottom. So I did 27 divided by 3, which gave us 9, and then 9 times 2 gives us 18. So I hadn't multiplied by pi yet, and then I take the 18 times that by pi, and that's where I got my decimal answer of 56.52.
Thank you.
Yep, no problem. Was there anybody else that had a question? All right, let's go ahead and go to the next one. All right, so now, again, there's composite figures in this section as well. So we have, and we'll be looking at a lot more composite figures come this following Monday, but find the volume of composite figures. So we have a solid composed of a right cylinder and a hemisphere as shown. Kind of looks like a silo, like a grain silo on a farm. So if the density of the solid is 100 kilograms cubed, what is the mass of the solid? All right, so this one's a little bit different. Now, this one includes us talking about density. So going back to science class, we had talked a little bit about density a while back. When we got into population density, I had put an equation on the board. I said we would come back and talk about density in the weeks coming up. We will be doing density. I'm not going to test you on density, but you should know that density is mass over volume. Now, some of you guys probably learned different ways. I think a lot of people said that they had teachers that did this. They drew a heart and then drew a line through it. Again, mass over volume. All right, density equals mass over volume. Now, we're going to use that here in just a minute, but before we can do that, we have to use that picture to figure out the volume of this figure. So we're going to have to do volume twice here. Now, I believe I already have this worked out, so I'm going to show the answer here because this one is an example from the textbook. I'll do another example here in a minute that isn't already worked out, but we have to find the volume of both of those pieces separately. So we would have to find the volume of the cylinder and the volume of the hemisphere. So that's what they did here in this first step. They used the equation of both a cylinder and a hemisphere, added them together, and they got our answer of 11.5. That's our volume. This is our volume currently. And then you had to use that to find the mass. So if we took the volume, multiplied it over to the other side, so it was mass now equals density times volume. You're just multiplying by the density, and you get the mass, which is 1,150 kilograms. So again, that one was already worked out in our book. Here is another example where we have a composite figure that's not already worked out. So this was one of the try-its in the book. Now, what is the volume of the space between the sphere and the cylinder? So they want the leftover space that's between those two shapes. So we're going to have to take the cylinder and subtract out the sphere. So our equations, again, you can write the equation for a cylinder a couple different ways, but essentially what we're doing here, we're going to do the cylinder minus, keep forgetting my P, minus the sphere. So for the cylinder part of this, again, you can use base area times height or just plug in the equation of a circle. So pi r squared times height. For the sphere, that's one we just learned today, 4/3. And this is a full sphere, so it is the 4/3, not just the 2/3. 4/3 pi r cubed. So now, only things we need to know are the height and the radius. So let's look over here at the figure. Well, we can easily tell the radius is 12. And the radius in both of these is the same because no matter which way you draw it, the radius will always be the same. So we could also draw it down. We could also draw it up. And the reason why I drew it both down and up is because now that is giving us the height of this figure. So 12 plus 12 is 24. So remember, the radius extends in every direction the same length for a sphere. On a cylinder, the bases, again, same thing's true about any direction on that two-dimensional plane of the base. So we have our height, we have our radius, and we just have to plug them in. Pi, the radius here again was 12, so 12 squared times the height of 24 minus 4/3 pi. R is 12 again, cubed. So now we have some simplifying to do. That's 144 times 24. We have 4/3 times pi 12 cubed. I don't know that one off the top of my head. It's a pretty big number. 12 cubed. Whoops, the wrong number. Cubed. 1728. So 1,728. Now, we still have a little bit more to do on the other side as well. We had 144 times 24. That gives us quite a big number over here as well, 3,456. I still have it multiplied by pi. On this side, let's go ahead and multiply by our fraction. So the 1728 times the top number is 4. divided by 3 is 2304. 2304. And then we can subtract those. 3, 4, 6, 5, 6 minus 2304. This could be my answer. And this is in centimeters cubed. That's in terms of pi. Or if I multiplied it out, 3.14, you could also say it's 3,617.28. Now, hopefully I did all the work right there. I'm going to show something else, and I want to see if anybody can tell me why this next thing should work. And let's use a different color so you know this is separate work. I'm going to do 2/3 pi r squared times height. All right. So taking this equation, we have our 2/3 pi. The radius again is 12, so 12 squared, the height. Oh, actually, sorry. I'm not going to do the full height. I'm going to do half the height. Let me erase that h. So I'm going to do times half the height. So this is also going to be 12. And now we're going to have 2/3 pi. 12 squared is 144. And then times 12 again is 1728. And then we're going to multiply by 1728 times 2 divided by 3. And I get 2 pi. So how is it that our answer over here is exactly the same? Can anybody spot what I did to come up with this answer? And I'll give you a hint. It goes back to the very beginning of this lesson. Any takers? All right. Okay, so in that equation there, we talked about 3 things that were closely related way back at the beginning of the section. It was the hemisphere, the cube, and the cone. On this diagram, we have the opposite happening of what we had earlier. If we just look at half of the figure, so just the top half of the figure, the top half of the figure should be, it's a cylinder with a hemisphere taken out. Same thing with the bottom. That leftover space would be the same volume of a cone with the same dimensions. So the equation that I use there is actually the volume of a cone, but 2 things had to happen. Because a cone form is 1/3 times pi r squared times height. This is the volume of a cone. So, yeah. Well, in this, we had the top half and the bottom half. So we had the area of a cone in the top and the area of a cone in the bottom. That's why it's 2/3 instead of just 1/3. And over here, where I had the height, when we're talking about what would be left of the cone, since we're talking about only half of the figure and the top half or the bottom half, we had to divide that in half, the entire height. So the entire height was 24, but the height that we needed was just for the top part or the bottom part. So it's going to be half of that, which was 12. So this was another way just to manipulate those formulas that we had at the very beginning. Again, if you didn't get that, that's fine. I just wanted to show how we could have taken the part from the very beginning of the lesson to also solve this with actually fewer steps. But again, if you weren't able to get it or you didn't see it right away, that's fine. Like I said, most of what we're doing right now, just basically plugging into formulas. So if you can plug it into formulas, you're pretty good for this section. Again, you have all the reference sheet formulas. So hopefully that'll be enough. This is that recap. This is why I was going back to that idea. This is that same idea that was back at the very beginning of the lesson. So the volume of a hemisphere is equal to the volume of a cylinder with the same dimensions minus the volume of a cone with the same dimensions. So we have, again, that relationship. You could also say that a cylinder is equal to the volume of a cone plus hemisphere together. So again, that's it. This is the assignment for today. There are a couple of questions for surface area, a couple of questions with volume. I didn't circle all the different parts there, but there are some on that first page and some on the second page there. So the second page is here. Actually, let me just circle them on here. So again, first part, it's going to be this entire column here. And then the second part is going to be this entire column here. So that's your assignment for tomorrow. Any other questions? Again, I'll be on tomorrow during my office hours from 12:45 to 2:15. I only had one person come on yesterday, but again, if you need help, I will be there. Again, if you don't see me on right away, give me a message on Remind because I'm just sitting with my computer open. But again, it's if I don't see you pop into the waiting room, just let me know through either Remind or through a text message. But that's it for today's lesson. Have a good day.